Few-shot non-line-of-sight imaging with signal surface collaborative regularization. Non-line-of-sight imaging aims to reconstruct objects out of the direct line of sight. Traditional imaging algorithms use dense measurements on the relay surface. For quick data acquisition, we reconstruct the hidden object with very few measurements, or imaging in few-shot scenarios. The problem of non-line-of-sight imaging is ill-posed. The bias in the physical model and measurement noise are two major obstacles for high-quality reconstructions. In few-shot scenarios, the lack of data makes the reconstruction task even harder. In the proposed signal surface collaborative regularization framework, joint regularizations of the estimated signal, the 3D voxel and 2D surface representations of the targets are designed. We show that the target can be reconstructed with very few measurements. In general, the reconstruction quality and the computation complexity of a non-line-of-sight imaging algorithm rely heavily on the physical model that simulates the measurement process. We adopt the linear physical model which only considers the square falloff of the photon intensity. The delta function describes the intrinsic domain of integration as the set of points with optical path length ct. In non-line-of-sight detections, the intensity of the back-scattered light is extremely weak after multiple diffuse reflections, making it impossible to measure the photon intensity directly. The recorded data are actually photon event stampings. For each measurement pair, n laser pulses are emitted to the illumination point and the recorded time resolved photon events are denoted by Boolean variables. By counting the photon events of each measurement pair in time bin, we obtain the photon event histogram, which approximates the value of photon intensity. To solve the inverse problem, the reconstruction domain is discretized with voxels. However, it is the surface of the hidden objects where photons bounced back that can be reconstructed. With this motivation in mind, we introduce the set G with the following property. For each pixel, I, j, in the horizontal and vertical directions, there exists at most one pixel, ij, k, with non-zero albedo value. The set G can be described equivalently by three matrices, namely, the indication matrix of foreground pixels E, the depth matrix D, and the albedo matrix alpha. The detection of photon events is assumed to be independent Bernoulli events and the probability of recording a photon event is proportional to the corresponding photon intensity. Using the Bayes formula, we maximize the posterior probability with the measured photon events. The set G is not convex, making the problem hard to solve. To overcome this difficulty, we also introduce the 3D voxel representation of the target, U, as the variable and maximize the joint posterior probability. Using the Bayesian formula, we obtain the SSCR optimization problem. The term gamma describes the joint prior probability distribution of the surface representation G, the voxel representation U, and the estimated signal tau. The collaborative regularization term plays a crucial role in the process of reconstruction. An ingenious design of this term not only results in faithful reconstructions, but also admits low-cost algorithms. In this work, we consider sparseness and non-local self-similarity of the target, as well as the joint sparse representation of the estimated signal and simulated signal. For the surface representation G, we use an implicit regularization upsilon, which will be made clear later. With these settings, we obtain the concrete optimization problem of the proposed SSCR framework, where G is the set previously defined, ds and dn are orthogonal matrices. There are 7 variables to be solved. The alternating iteration method can be employed to deal with this problem. Detailed discussions of the solutions to the subproblems and the choices of parameters are provided in the supplement. Note that the implicit regularization term upsilon, G, only appears in the subproblem of updating G. Intuitively, for any fixed voxel representation of the target, we wish to choose an element from the set G which is not only near the given voxel, but also acts like the surface of some real-world object. With this motivation in mind, we construct a map S that assign an element in the set G for each 3D voxel and call this process surfaciation. Pixel-level correlations are used to improve the reconstruction quality. More details are provided in the article and the supplement. The proposed method is tested under both confocal and non-confocal datasets. For the instance of the pyramid, the simulated confocal signal is detected at only 3 by 3 points. The three views of the reconstruction results of the LOGBP, FK, LCT, DLCT, SOCR, and SSCR methods are compared in the middle. The SSCR method reconstructs the target faithfully. The figure on the right shows that the FK solver with interpolated signals cannot reconstruct the target correctly. For experiments with real-world measured datasets, we use the confocal signals for the instance of the statue from the Stanford dataset. A subset of 5 by 5 signals is subsampled for the reconstruction. The oracle is generated with the SOCR algorithm with 64 by 64 signals. The SSCR algorithm provides the best reconstruction results in terms of both visual quality and albedo PSNR. For non-confocal experiments, we use the simulated signals of the letter K in the NLOS benchmark dataset and the signals of the figure 4 provided by the work of the phasor field method. The oracle is generated with the SOCR algorithm with 64 by 64 signals. The SSCR algorithm outperforms existing methods in terms of albedo PSNR, and the reconstructions contain very few artifacts in the background. In conclusion, we have proposed a signal surface collaborative regularization method for few-shot NLOS imaging scenarios. The proposed algorithm enjoys low complexity in few-shot NLOS scenarios, but the L1 regularized subproblem takes iterations. Besides, the reconstruction results may be improved with noise modeling and incorporating other regularizations. Finally, we end this video by summarizing the flowchart of the proposed SSCR framework.